Hello friends, welcome to the channel of Digital to Real. Today we are going to do the Verilog coding for carry look ahead adder. This is the circuit for the carry look ahead adder which we obtained from our last video of carry look ahead adder. I will provide in the description box the link for the same. I start the video with the assumption that you have gone through the basics of carry look ahead adder. Now here actually I assume that there are two inputs A and B, each of them of 4 bits. Okay, and this is the P0 carry propagate and G0 carry generate for the first 2 bits. Here it is the propagate and generate for second 2 bits. Here is the propagate and generate for the A2 and B2. Here is the propagate and generate for the A3 and B3. And here S0, which is the XOR of P0 Cin, S1 which is the XOR of P1 C1, S2 which is the XOR of P2 C2, S3 which is the XOR of C3 and P3. The input to the circuit is the Cin, also the carry input from the outside or the previous stage, and these are the input lines A and B, each of them of 4 bits. So output of the circuit is S3 down to S0. Input to the circuit is A and B, each of them are 4 bits, and Cin is the input carry, and output of the circuit is S3 to S0. Now for a single bit full ladder, let it be for the 0th position of A0 and B0. So the generate carry, the carry which is generated from the full ladder is equal to C0 equal to A0 dot B0 plus Cin dot inside the bracket A0 exclusive or B0. This equation I can generalize and write it like this: Ci is equal to Ai dot Bi plus Ci minus 1 dot inside bracket Ai exclusive or Bi, where I stand for the ith bit of the adder, means ith bit. Suppose there are 4 bits, A0, A1, A2, A3. So I stands for A0, I stands for A1, I stands for A2, I stands for A3. And so this is a generalized equation where Ci is equal to addition of 2 terms. First term is called the carry generator, where the Gi, we write it as Gi. Gi means generate carry generator. There is no dependency on previous stage carry, so it is called carry generator. While in the second term, Ci minus 1 dot Ai exclusive or Bi. So this particular term is multiplied with Ci minus 1, okay, to give Ci. So here there is a dependency on previous stage carry. So this is called the carry propagated and it's represented by Pi. So I write a equation like this: Ci is equal to Gi plus Pi multiplied by Ci minus 1. Now let's generate carry for 4-bit carry look ahead adder. So I is equal to 0. So C0 is equal to G0 plus P0 Cin. This is the equation. I is equal to 1. C1 is equal to G1 plus P1 C0, and C0 can be replaced with this expression, and the final value is G1 plus P1 G0 plus P0 P1 Cin. Then I is equal to 2. Okay, so C2 is equal to G2 plus P2 C1. C1 is replaced with this big expression, so G2 plus P2, and inside the bracket G1 plus P1 C0 G0 plus P0 P1 Cin, close bracket, and the whole equation on expanding is coming as G2 plus P2 G1 plus P2 P1 G0 plus P2, P1, P0, Cin. For I is equal to 3, C3 is equal to G3 plus P3 dot C2. C2 is replaced by the previously we got the C2 expression, and final equation is like this. G3 plus P3 G2 plus P3 P2 P1 plus P3 P2 P1 G0 plus P3 P2 P1 P0 Cin. This is C3. Now we will see the sum bit. So S0 is equal to A0 exclusive or B0 exclusive or Cin. For even a single bit full adder, sum bit is actually the exclusive OR of all the bits. Okay. So S0 can be written as A0 exclusive or B0 is P0. So P0 exclusive or Cin. S1 is equal to A1 exclusive or B1 exclusive or C0. So S1 is equal to P1 exclusive or C0. S2 is equal to A2 exclusive or B2 exclusive or C1. So S2 is written as P2 exclusive or C1. S3 is equal to A3 exclusive or B3 exclusive or C2. So S3 can be written as P3 exclusive or C2. P3 is A3 exclusive or B3. So starting with the Verilog code. Take time scale 1 nanosecond by 1 picosecond. So the time scale, what it does is specify the time precision of a module, and simulation time and delay values are measured in correspondence with the time scale. Now I have actually commented defined delay #10. I have commented module CLA underscore adder. So this is the module name. What is the port list? INA, IN1, comma IN2, both the inputs to the adder, carry in previous carry, comma sum is the output, comma carry out is the output, bracket close, semicolon. Parameter I have mentioned data underscore width is equal to 30 semicolon. Data width for in1 and in2. So this generalized I have put it as 32. I can make it 4, 16, 8 from the test bench. I can modify the parameter data width. Okay. So at present by default it would take the data width 32. Parameters are constant values which do not belong to any data type such as register or net. So input bracket data underscore width -1 down to 0, bracket close, square bracket, in1 semicolon. Input bracket data underscore width -1 down to 0, bracket close, in2 semicolon. Input carry underscore in semicolon. Output, that is the sum, data minus underscore width -1. It is inside the square bracket down to 0. And output is the carry out, semicolon. So input and output we have mentioned. Now we are declaring the wires. So gen and pro, what are these? We spoke about the generate carry and propagate carry. So that generate carry and propagate carry, I am declaring them as wire, and the width of the generate carry gen is inside the square bracket data underscore width -1 down to 0, bracket close, and propagate carry, that also it is of width square bracket data underscore width -1 down to 0. Actually the data width of in1 and in2 would be same as gen and pro, generate carry and propagate carry. Now there another carry underscore temp variable I am declaring. Okay, that is of width actually one more than the data underscore width -1 down to 0, one more bit. So it is data underscore width down to 0. Why it is more? Because we are generating initial carry, we are keeping the carry underscore in, that is the initial carry plus the number of carries generated for each stage. So it is number of carries +1, and that +1 is for the initial carry. Now we are going to use the generate in the Verilog. So in order to use the generate and engenerate block, I am declaring two variables j and I as gen var semicolon. Okay, and this two variable will be used for loop inside the generate block. So we assume that the carry underscore temp of 0 is type to carry in, that I have just now told. Now here is the carry generator. What I am doing to generate the carry. Now here is a for loop which is using the variable j. J is a gen var variable type, and because it is inside the generate block, it has to use the gen var variable only. It cannot use integer. So for inside bracket j is equal to 0 semicolon j less than data underscore with semicolon j is equal to j plus 1. Begin. I am doing a labeling for this generate for loop, and the label name I put it as carry underscore side underscore CLA. Now here I am generating assign. So gen and pro both are of wire type, so I can use the continuous assignment here. Assign gen inside square bracket j is equal to in 1 inside square bracket j and in 2 inside square bracket j. So it is the AND of in 1 and into jth bit. So continuous assignment pro j is equal to in 1 j exclusive or in 2 j. Here is the exclusive or operator. Now continuous assignment for the carry temp. Okay. Carry temp I am writing as j plus 1. J plus 1 because jth 0 bit is meant for carry in. Okay. So when it is 0, then it would be carry underscore temp 1. Temp 1 is actually the carry underscore temp 1 is the carry generated for the 0th bit. So gen j is the gen j or operator. Plus was there in the equation, so plus is actually or operator. Propagate carry j and pro j is the propagate carry j and carry underscore temp j semicolon. So gen j is equal to in 1 dot into, that is AND operator is there, and pro j there is actually the in 1 XOR into for jth bit and then multiplied by carry temp of j, previous carry, semicolon, and here is the end for the begin statement. Now is the carry out. So carry out, how I will get the carry out? So the last carry, that means assign carry underscore out is equal to carry underscore temp, and the last bit inside the index what I will put data underscore with. So carry temp was from data underscore with to 0. So that was the range of carry temp. That was the width of the carry temp. And the most significant bit, the MSB, that would carry the carry out bit. So continuous assignment I am doing for carry out in this way. Now calculate sum. In order to calculate the sum, again I am using a for loop inside the generate block. Please note, this for loop is separate, other for loop is separate, and this for loop is using the gen var variable I. Earlier one was using gen var variable j. So for I is equal to 0, semicolon I less than data underscore with, semicolon I is equal to I plus 1. And the bracket close. Begin end is also here, and for this begin I am doing the sum underscore side underscore CLA. This is the label of this particular for loop. This is meant for calculating the sum, that is at the output side. So assign, continuous assignment is happening, is equal to sum of I is equal to in I input 1, actually it is input 1 I exclusive or in 2 I exclusive or, carry temp. Okay, this is for some bit. That is 2 input. If it is in 1, in 2 and carry in. So in 1 ith bit exclusive or into ith bit exclusive or carry underscore temp. I means it would carry the carry in bit. Okay, previous carry. For the first stage it would carry the carry in bit. For second stage when it is 1, this is also 1. 1 is for the previous stage. 0th carry underscore temp from the previous stage. Okay, that would be exclusive or with the in 1 and in 2 and will give the sum here. Here is the end generate and here is the end module. For generate keyword I have the end generate here, and for module I have the end module here. This is the RTL code. Now inside the generate for loop, okay, for variable j, that was used, variable j means j was of type gen var. So inside the for loop what was happening is that as the parameter value of data width is 32 sets of carry underscore side underscore CLA was getting generated. 32 sets means in each set we were generating the gen, pro and carry temp. Okay, so for 32 bits of in 1 and in 2, for every respective bit, okay, we were generating the gen, pro and carry temp using the label carry underscore side underscore CLA 0, then carry underscore side underscore CLA 1, gen 1, pro 2, pro 1 and carry temp 2. This way 32 sets were getting generated. Hardware will translate the code into this way. Now generate for loop with variable I. Okay, the variable I was used for the for loop for the output side, that is the generation of the sum side. So it was generating 32 sets or copies of synthesizable hardware for sum underscore side underscore CLA. This was the label for the generate for loop. So how it would generate the sum for the hardware? Sum underscore side underscore CLA 0 dot sum 0, sum underscore side underscore CLA a dot sum 1. In this way it would generate the 32 sets or copies. Generate for loop generate instances for each loop of variable. So it explicitly mentioned the hardware. Generate for loop is not inside the procedural block. So it is not inside the always block or initial block. It is never inside the procedural block. If you like to know about more about the generate for loop, please see the link of the generate for loop provided in the description box. Now we will go through the test bench code for carry look ahead adder. So tick define delay #10. So delay I have mentioned here and this delay I will using in the code. Tick define. So module CLA underscore adder underscore TB bracket semicolon. So CLA underscore adder underscore TB is the name of the module for the test bench. Inside the module parameter data underscore width is equal to 16 semicolon. So here the data width is 16. It would override the 32 bit of data width in the RTL code. So we can override the parameter from the test bench. Now reg carry underscore in. Okay, reg carry underscore in is the carry in. Okay, it is of registered type, and reg data underscore width -1 down to 0 in1 comma in2 semicolon. Okay, so inputs they are of reg type and they are with data width -1 down to 0. Now parameter values can be overwritten during the module instantiation. Okay, that is what this parameter will be overwritten when we will instantiate the CLA adder. So here it is there, CLA underscore adder. This is the CLA adder, carry look ahead adder. The instance is CLA1. This is the instance name. This is the module name of the RTL. Okay. Dot sum is tied to sum data underscore with -1 down to 0 bracket close semicolon. Okay, this is the CLA adder sum bit. It is tied to the sum bit of test bench. Dot carry underscore out, that is of CLA adders carry out, that is tied to the carry out of this test bench. Input 1 and input 2. In 1 is tied to the in 1 data with -1 down to 0. This in 1 is of the CLA underscore adders in 1, and this in 2 is also CLA adders in 2. These are the ports of that CLA adder, and it is tied to inside bracket into data with -1 down to 0, and then there is a carry in that is also in the port list of CLA adder, that is tied to the carry in of test bench. Okay, now this is the initial begin in statement where in 1, in 2 and carry in are initialized. 16 tick D 0 semicolon, that is for in 1, in 2 is equal to 16 tick D 0 semicolon, carry in is equal to 1 tick D 0 semicolon, and here is the end for this begin. Okay, now after the initialize, not after this initial begin and this initial begin end will run concurrently. Okay, initials and always block, they run concurrently. Now I will wait here also. What we will do, we both will be starting at the 0 simulation time, but here in this initial begin and I will wait for tick delay, 2 tick delays, and then I will provide in 1 is equal to 16 tick D 0 semicolon. After again hash tick delay, which is 10 time units, into I am providing a 16 tick D 20 semicolon. So I will provide the combination of inputs for addition as I like. So hash tick delay in 1 is equal to 16 tick D 20 semicolon. Again I have next statement hash tick delay. Here also again I have changed in 1 is equal to 16 tick D 30 semicolon. In 2 is still same at 16 tick D 20. So in 2 has not changed. I am only changing the in 1 and adding it with the in 2. Next statement is hash then tick delay into 3, that means 30 time units. After 30 time units again in 1 I am changing. Here I have put hexadecimal value. You can put the 16 tick value, whether hexadecimal or the decimal value, whatever you like. So here in the beginning I have put the decimal value, then the hexadecimal value 16 tick H, all F's, and into again I am applying after hash tick delay into 3, means 30 time units, and I am providing at 16 tick H 7 triple F semicolon. Here is the end for this begin end block, and here is the end module for the final module test bench. Okay, please note this is the combination of input. Whatever you want to add, you apply to the RTL circuit and check the value of carry out and the sum bit to find out whether the addition matches or the carry look ahead adder does the purpose of proper addition or not. If you like the video, share with your friends. Please subscribe the channel and have a very nice day. Bye bye.